The Institute of Eminence scheme has been launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one of the select institutes of excellence. As part of our commitment to the cause of fostering world-class research, IIT Madras has set up a number of research initiatives in diverse fields of contemporary relevance. Many of these initiatives will go on to become centers of excellence within the IIT Madras system. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway. As part of these initiatives, it is proposed to host a series of webinars from each cluster to showcase the innovative research being generated to various stakeholders like researchers, industrialists, and policymakers. These webinars will give an opportunity to engage in conversation with eminent faculty from IIT Madras and other international researchers, and also to find more collaboration in those research areas. So why wait? Click the link below to be a part of this.
Chennai transports almost 800 million liters of water every day, out of which only 400 liters is being charged. Other 400 million liters per day is lost in the form of leaks and pilferage. From our survey, we found that most of it goes into leakage, and since the pipelines are underground, there is no way of telling where the leakages are. Endobot is a robotic device which can travel inside underground pipelines to identify various types of defects.
Other than water pipelines, Solinas has also developed similar devices that can be used in oil and gas pipelines. It is the recent access to open source electronics that has made such robotic automations possible at an affordable price.
A 12-feet minaret on the Darwaze-e-Roza of the Taj Mahal was blown away by high-speed winds in Agra on Wednesday.
Unscientific interventions are responsible for decay in a shorter period of time than their thousands of years of existence.
Although study of materials used in heritage monuments and other structures is not new, there was little R&D in the area of structural and engineering aspects of these heritage structures until the National Center for Safety of Heritage Structures was set up inside IIT Madras in 2013.
We're working with a large number of historical monuments in our country, across the length and breadth of the country, and not only in India, even abroad.
Actually, we have a very good world-class gym facility.
Thanks for the lovely video, Shivram. I mean, IIT Madras, it's a big ocean. It always good to know a lot more about IIT Madras always. So a very good evening to everyone who present virtually through Zoom and YouTube. This is Rudra from the Office of Global Engagement, IIT Madras. As you all know, the IRIS webinar is gaining a momentum in the public domain. I'm very happy to welcome you all for the 32nd webinar of this IRIS webinar series. Today's webinar is on advanced laser material processing under the cluster advanced manufacturing. So this research initiative project is being led by Professor G.L. Samuel. So to introduce Professor Samuel is currently working as the professor in the Department of Mechanical Engineering, IIT Madras. Also, he worked as the postdoctoral research fellow at Department of Mechanical Engineering, National University, South Korea during the year 2003 to 2005. His research interest includes conventional and non-conventional manufacturing, metrology and computer-aided inspection, micro machining, CAD, CAM. His publication include 43 international journal papers and 49 national international conference papers. So Professor Samuel will be in charge of non-machining, metrology, and characterization aspects of the proposed Center of Excellence. Having him as one of the speakers of today's program, we also have Professor Ramesh Babu. To introduce Professor Ramesh Babu. Ramesh Babu is the founding member of Advanced Manufacturing Technology Development, AMTDC, and distinguished faculty of V. Balaraman Institute Chair Professor. Dr. Ramesh Babu received his PhD from IIT Madras in the year 1990. His research interest includes manufacturing technology, grinding, abrasive water jet machining, sheet metal fabrication, laser beam machining, CNC, PLC, and robotics, precision machine tool development, process modeling, and simulation of manufacturing systems, and a lot more. His publication includes 61 international journal papers and 104 national and international conference papers. Professor Ramesh Babu will be the overall in charge of the research in the ultra short pulse lasers, interaction, and the development of indigenous manufacturing facilities. So also we have Professor Satish T.S. Bukkapatnam as the moderator of today's program. To introduce Professor Satish, he received his PhD and MS degree in the Industrial and Manufacturing Engineering from the Pennsylvania State University. He currently serves as the Rockwell International Professor with the Department of Industrial and System Engineering Department at Texas A&M University, USA. He is also the director of the Texas A&M Engineering Experimentation Station Institute of Manufacturing Systems. His research in smart manufacturing addresses the harnessing of high-resolution non-linear dynamic information, especially from wireless MEMS sensor, to improve monitoring and prognostics mainly of ultra-precision and nano-manufacturing process and machines, and wearable sensors for cardiorespiratory process prognostics. So he will be collaborating in the research works focused under the PCOE Advanced Laser Material Processing. So before we start, we have two important announcements to the audience. One is the long-awaited announcement regarding certificates, which will be announced during the end of this webinar. So stay connected. The other one is regarding Q&A. So please use the Q&A to enter your questions and upload questions that interest you so that the moderator can prioritize them. Over to you, Professor Satish.
Good evening, everyone, and good morning and good afternoon for those who are tuning into this webinar from abroad. And welcome to everyone. Again, it's a great pleasure to be part of this joyous occasion and become part of this webinar. And I would be serving as the moderator of this session. As Rudra nicely mentioned, feel free to ask any questions through the chat, and I will try to moderate and then talk to and interact with the speakers as we go on. And without further ado, we will get started with the sessions, but I would like to provide a few personal pointers on the context of this webinar for the benefit of everyone. The Center for Laser Processing is a strategically important center for excellence for any nation. And I'm very pleased that Professor Samuel and Professor Ramesh Babu are spearheading this important initiative. And if you look at laser material processing, it is not just pertinent for the conventional or non-traditional manufacturing alone, but directed energy is becoming extremely important in domains extending beyond manufacturing, especially in the strategic sector. And also with the growth in the additive manufacturing and related technologies, the use of laser material processing as well as the underlying foundations would be extremely essential. So therefore, I would request everyone to keep this broader context in mind as the presentations proceed, so that the question and answer sessions, as well as my job as a moderator, will become that much more enriching. So with that note, let me turn it over to Professor Samuel to begin this wonderful webinar. Professor Samuel, over to you.
Yeah, good morning, Professor, and good evening to the participants who are in India. So we thank you and we welcome you all for this webinar series. So we'll be talking, we'll be organizing and we'll be speaking on behalf of the webinar series, which is being conducted as a part of Institute of Eminence. So under the main heading of Advanced Manufacturing, and the name of our center is Center of Excellence for Advanced Laser Material Processing. So we need to thank our government and Department of Human Resource Development, MHRD, for giving IIT the status of Institute of Eminence. So we thank our director, deans, and all the team. So we have been helping in building up these centers of excellence. So this center is a part of advanced manufacturing technology. So today we'll be looking at the some of the fundamentals about lasers, and then we'll be looking at some of the applications of lasers and the work which we propose to do in this center. And also we'll be introducing you to the team who are working. And also we have an exciting a small quiz for all of you, and we'd like to understand what is your level of knowledge about the lasers. So you may ask, okay, do the quiz after the seminar, but that's not the thing. So we are going to do it right in the beginning of the seminar to see how you will do it. So if you talk about lasers, light amplification by stimulated emission of radiation is a very, very interesting phenomena. So right from my childhood, I've been fascinated by these lasers. So now I got an opportunity to work in this. So I thank God for that. And then if you look at the background and the history, so in this phenomena of coherence and then lasers was found in the beginning. So they made a statement telling that, okay, it looks like a very interesting phenomena, but without any applications. But now today, with a standpoint where we stand and look at the number of applications, so what are being done with these lasers. So right from starting from the laser pointer, what as a teachers we use almost every day, to big phenomena like Star Wars, where they wanted to take a very powerful lasers and focus it even on anything which can be destroyed. So even asteroids, they're coming and close to the earth, so you can focus very powerful lasers and then you can evaporate it before it reaches the earth. So that is the kind of way how these lasers have been moving. So now before we proceed, so we thought we'll have a simple quiz. I think our technical organizers will be popping you up the questions. So if you are familiar, or if you at least know, you can guess some of the answers. They are very easy to find. So quickly we'll go through that, and then later I'll be continuing my talk. Yeah, the first question is up. So who invented the first working laser? So you can click on that. Okay, just a few seconds we'll give, and then we'll be moving on to the next question. So we don't need to take much time. Second question. Yeah, the first theory of laser principle was proposed by. Okay, we'll move on to the next question. Yeah, who was the Indian scientist who developed the first working carbon dioxide laser, CO2 laser? I think you should be able to answer this question. Okay, we'll move on to the fourth question. Okay, what is the working wavelength of excimer laser? So which category it falls under? Okay, we'll move on to the final question. Population inversion in ruby laser is achieved by what? Yeah, I think the organizers will tell you who. Can you show the answers? We'll see who has answered it right, all the questions. Okay. So for the first question, Theodore Maiman, Chandrakumar Patel, very less number, so we know less about our own country. John Manday, so 70 out of 98, none of the above 15. Okay, yeah, thank you for your participation. So maybe the organizers will look at who answered all the questions right, and probably they will reward you. Thank you very much for your active participation. So we'll move on. So if you look on to the history of lasers, even long before the lasers were found, so Planck has given a statement, so relating between the energy and the frequency of radiation, so which actually happens in laser and which was invented later. And even Einstein has talked about the stimulation of emission, and the inventions go on. So several people actually have contributed for finding the lasers and then bringing to the level what we have today. So Charles Townes is another name which is associated, and there were several patents in US and other countries, so which have developed. And finally, so we are in the state what we are talking about. So when you look at some of the laser applications, you'll wonder how so many applications we are able to develop. And then when you look at the lasers, we can divide them into different categories based on the way how they are produced. But for me, I have divided it into three categories, like continuous lasers, then short pulse lasers, and ultra short pulse lasers. So where the pulse lasers are more powerful than the continuous lasers. So I think they tell an example, like if you want to break a stone, so you can do by two things, either take a big hammer and then hit it powerfully, otherwise take a small hammer and hit it several times. So thus, in both the ways, we can break the stone. So here, the pulse lasers are very, very powerful, and they are available in all the ranges, right from ultraviolet, where you can't see, and then even in the visible range, and even in the invisible range they are. But in invisible range, they are very dangerous, because there were researchers who were even almost lost their eyesight, because when they fire the laser, they can't even see that. So that is the reason for safety. What generally they do is that they combine it coaxially with another visible light, so that you can see some light is coming, and then you will try to avoid that one. So that's the way how these lasers work. And when we talk about these ultra short pulse lasers, so they are in the range of 10 to the power of minus 13, 10 to the power of minus 14, and like pico and femtoseconds. So to understand how short is this, so when we look at the distance between the sun and the earth and the time it takes, about 500 seconds which it takes. So now the same light which is traveling at almost 3 meters per second time, the time required to cross the hair. So how much time it will take? So that short is the time range what we are talking here. And when you look at the power which these lasers generate, they are very, very powerful because the energy what we put in one pulse. So usually we have the pulse energy of 40 microjoules, and then we put it in a time period of 1 into 10 to the power of minus 40. So here, if you take micro, then 10 to the power of minus 6. So now you cancel these 6 zeros. So finally, the resultant will be something like in the order of 10 to the power of plus 9 plus 10. So gigawatts of energy will be able to get instantaneously by using this kind of pulsed lasers. And they are so powerful that when you put them on even the hardest material, so they vaporize it even before the heat actually passes into the bulk of the material. So this phenomena has been very much used in machining of various materials. And then we can see here the diagrams, how continuous lasers and short pulse lasers, actually when they interact with the material, we find that some of the heat is absorbed here, and then we see what is called as a heat affected zone. But with ultra short pulse lasers, so they give a very clean kind of a cut. So where you can see here how clearly the machining is taking place. So thus, the shorter the pulse duration, so the cut what you're going to get will be much, much better. And then if you try to understand the laser matter interaction, so this is a great phenomena, so which actually happens when you put a short pulse laser. So when you put the short pulse laser, the top layer, which is having the free electrons, will actually absorb and then they get heated up. And the heat is so much that before the heat reaches the bulk of the material, so they quickly evaporate and the material is removed. And that is the reason you can get a clean cut, what you see here, by using the ultra short pulse lasers. And when we talk about modeling of this kind of a ultra short pulse laser, and then if you try to study the laser matter interaction, so something great is happening here. When we put the laser, instantaneously, the temperature of the electrons, as is shown in the previous figure, so shoots up to a very high extent, and then it starts cooling. But the lattice temperature, the bulk temperature, slowly it will be increasing because there will be not much time for the heat to be transmitted. So thus, this kind of a phenomena can be modeled only by using what is called as a two temperature models. And then when we put continuously several pulses, so how the lattice and the electrons react, we can see here. So the temperature shoots up, so then it will be trying to come down, and immediately we'll be putting another pulse here. So again, the temperature shoots up, and this is the way how the material reacts to the pulses, and the material is being evaporated and being removed. So my student, and then along with Professor Shanmugam, who is emeritus professor, and we joined this webinar. So we have been working on modeling of these kind of laser material interaction to see how much material is being removed when you put a pulse on the material. So we have taken titanium alloy, Ti-64, and then we removed the material, and then we actually made a cross section and took the how much volume has been removed, and then we modeled it, and we have been comparing. So this work is still being continued. So similarly, not only drilling the holes by using this, we can do even milling of the channels and other profiles by using the ultra short pulse lasers. When you look at drilling, we can carry out several types of drilling. Precursion means we put several pulses at the same place. So then the material is going to be removed. But if you want to remove a big area, we can actually pass the laser in a particular path and then we can remove the materials. If the material thickness is more, we can go in a cyclic way and we can remove the materials. So thus, along with the removal material, we can combine the other technologies of moving the lasers at a very precise level, and we can achieve profiles, different profile shape profiles with a high precision. So some of the applications of it is, we have been working on this research project where making the micro holes for the coolant holes in the blades of the jet engines. So where the jet engine blades need to be cooled, otherwise for the temperature, the working temperature, they will get melted. But by using the coolant holes, a high pressurized fluid will be circulated and the blades are kept cool. So in this center, so at IIT Madras, we have developed actually a system with an ultra short pulse laser. So where you can see this here. And we have been planning to make it as an hybrid machining where with the EDM, electrical discharge machining, we make the holes and then we finish them with the ultra short pulse lasers. So the ultra short pulse machining is something like the scalpel of a doctor, where if you want to cut an eye, so he can do it very precisely. So that's the way how the ultra short pulsed lasers work. And then we can finish the holes to get a highly accurate and precise holes. So these are some of the experiments what we have conducted, and now we have published some of the results. And then another interesting work what we have been carrying out and will be continuing in the future is the micro machining of micro channels and silicon. So generally when we were in the school and in the college, so they told that the lasers cannot cut highly reflective materials and highly conductive materials like aluminum. That's because the heat is absorbed. That is true with the continuous lasers, but with the short pulse lasers, even we can cut highly reflective materials and conducting materials. So this is what we have seen here in the micro machining of laser silicon. So this article has come in the Tech Talk. So probably our organizers will put the link so you can read the article on the IITM Tech Talk. And also another interesting phenomena, what we have observed here is the surface, the bottom of the channel, we can see a very systematic pattern. So it is called as laser-induced periodic surface structures. So which are being of great interest these days to produce different types of structured surfaces. Because whenever we want a special properties for the materials, so now we see what is called as a hydrophobic and hydrophilic surfaces. So where in some places, like in the lotus leaf, we don't want the surface to be wet. So for that, we can make the texturing and then we can achieve it. So we have been working on this area. So we have made these kind of textures on the tools, and then we found that the friction was reduced and the efficiency of machining has increased to a great extent. And also we have been working in this problem of texturing various materials to achieve hydrophobic and hydrophilic kind of surfaces in collaboration with University of Technology, Sydney, Professor Dongbin Wee. So as we move on, we also see some of the applications of these kind of texturing on solar panels, aeroplane wings, so where we don't want the ice to form there during the winter, and also in biofouling to make the surfaces like anti-biofouling so that the fungus and algae will not stick to the surface. So all these things we can do by making the texturing. And not only in that, so we have been working with Deakin University with Professor Ling Soo Kong. So where we have been trying to put the textures at the bottom of microfluidic devices. So where we'll be able to achieve the separation of the flow or mixing of the flow in a much efficient way by putting the textures at the bottom of the microfluidic devices. And also we are working in collaboration with Professor Sasaki from Hokkaido University in Japan to produce the nanoparticles. See, when we put the laser, it will be ablated and a flume will be formed. And when it bursts, so that energy actually is being used to burst the material and the nanoparticles are being formed. So we have been utilizing this kind of a process to produce nanoparticles. And even in the future, so we have been procuring, actually it's under the process to produce 2 kilowatt laser for laser welding and also for 3D printing of metals. So these days, so 3D printing of metals have been achieving a great importance because they have a lot of practical applications. So another area in which we are planning to work is the laser shock peening. So by using which actually we can enhance the properties, particularly the fatigue strength of the materials. And thus, when you use some of the gears and other parts which are subjected to fatigue, so when you subject them to shock peening, so they'll be relieved of the internal stresses and they work much better. And since we don't have much time, so I'll take just few more minutes to talk about the measurement and characterization of these micro features because they're very important. So not only producing these micro features, but characterizing them is a very important one. So Lord Kelvin said, unless you measure, you cannot make it. Unless you measure, you cannot make it. So somebody may make a nano hole, but if you can't measure and prove it, so it is we can't characterize it. So thus, we have actually characterized our micro features by using several instruments like optical profilers, using the white light interferometry. Then we have also used the laser scanning confocal microscopy to find out what is the profiles, what is the material which has been removed. We also used the atomic force microscope and to see the micro or the nano level material, how it has been removed. We actually tried several methods and finally we could actually arrive almost very close to the amount calculation of estimation of amount of material which has been removed. But still we had a challenge when we wanted to characterize the cylindrical holes which are of a like few millimeter depth. We couldn't find any instrument because the probes cannot go into those holes. And when the walls are vertical, so the light won't get reflected and you can't get back the images. So thus we tried all the instruments, we couldn't succeed, but finally we were able to do that by using computed tomography, like in the medical, they do take the CT scan. Similarly, we can do that for metals. So we have actually nano tom CT. So where even if the holes are micro cylindrical holes, so we can take the cross section, several sections of it, and then geometrically with the software, we can combine them and reconstruct the cylindrical holes which are internal, so which you can't see from outside, but we can reconstruct them like that. And then we can characterize, finding out the circularity error or the cylindricity error. So these are some of the areas so on which we are planning to work and we have been working. So that the center is something unique where we are trying to put all the facilities like continuous lasers, nanosecond lasers, and femtosecond lasers, then characterization and measurements, metrology, and even modeling and under one umbrella. And this is the mammoth task. It can't be done by a single person. So we have a big team helping us for eminent in their respective areas. So Professor Ramesh Babu sir is going to talk about not only just the research, but how to take it to the next level of making it into a product after my talk. Professor Nilesh Vasav is currently the Dean of Students here. So he's going to talk about, maybe in the next series, he'll be talking about laser deposition and other phenomena. Professor Fani Kumar from Metallurgy and Materials. So he's expert in laser welding. And Professor Amitav Ghosh, so mechanical micro brazing of the tools. So he'll be talking about that and he'll be carrying out the work on that. Then Professor Sivaramakrishnan from Physics, so has been helping us in modeling and understanding the laser material interactions at the nano level. We also have the strong collaborators from national and international level have been working. Professor Satish Bukkapatnam is here with us. And we have Professor Rodovan. And then we have Professor Narendra Dahotre in Texas, University of North Texas. And Professor Rajurkar, Professor Sasaki from Japan, Dongbin Wee from UTS, and then Professor Ling Sukong from Deakin University in Australia, and Dr. Ravi Bate from ARCI Hyderabad. So he has also joined. So we have been collaborating, and we have a strong workforce of our research scholars who have been working day and night to do this possible. And those who are participating, you may ask how we can participate in this. Yeah, you have an opportunity to interact with this center. So we have been inviting young international faculty. So you can encourage faculty from other countries to come and work here for a short period, 6 months or 1 year. And also we have joint doctoral programs. So you can join with other countries and then we can work, student exchange programs, internships, workshops. So those who are in final year or third year, after that, we can give you, in the current situation, virtual internships. You can all participate in that. So we look forward to great interaction with you. And we thank all the participants for taking time to listen and then actively participating in the quiz. Thank you, one and all. So we'll keep the time for the question and answers at the end of Professor Ramesh Babu sir's talk. So now I'll hand over the mic to Professor Satish Bukkapatnam, who is the moderator.
Thank you, Dr. Samuel. That was a very interesting presentation, and it was thrilling to learn the breadth of activities proposed and underway at IIT. And of course, I'm not surprised given the strength of the team, as well as the leadership that's coming together to enable this center. And also, it's a great pleasure to be part of these activities, and glad to see many of my eminent colleagues also getting involved in this type of a strategic activity. And as I mentioned earlier, this center would not just advance the manufacturing technology from a non-traditional manufacturing as well as emerging additive manufacturing realm, but also it will have significant impact in the measurement and metrology area, as well as characterization and strategic pursuits that are critical for the nation. So the questions that we see are pretty much in that direction, but as Professor Samuel mentioned, we'll hold off on the question. But what I would like to do is take this opportunity to introduce my great friend and a leader, Professor Ramesh Babu, for the next session. And Professor Ramesh Babu is considered to be one of the eminent people in the manufacturing area from India. And in fact, his center has been the envy of many of us in the US for the simple reason. We at the universities as well as institutions of eminence across the world, we focus on R&D at low TRL level. And very few of us have succeeded in translating our research into various industry level aspects, because there is considered to be a valley of death between fundamental research and its application. And Professor Babu, I consider as one of the very few who have successfully bridged this fundamental research and its translation. And I hope everyone gives his seminar a listen and understand what goes in the mind of the leader to enable this translation of this fundamental research into the impactful industrial applications. And he has made significant contributions to the area of micro manufacturing and also in precision engineering. And I have had a chance to host him at Texas A&M on multiple occasions. And as you may gather from his resume, he was serving as an eminent visiting fellow at our center for 2 years. And I have also had the fortune of attending and basically taking a tour of his center on multiple occasions, and participated one summer as part of the GYAN activity to deliver courses in data science applications in manufacturing. With this type of an interaction, I have no doubt in mind that this talk would be of great interest and great impact to those of us who are participating. So with that introduction, I would like to call Dr. Ramesh Babu to give his address. Dr. Babu, over to you.
Thank you, Professor Satish, for a very nice introduction. But anyhow, I just wanted to share my thoughts about each of the speakers, like the moderator as well as the Samuel. So they have been associated with many of our activities over the last few decades. As a student of IIT Madras, Dr. Samuel, and also Professor Satish, and his mentor, Professor Ranga Kumanduri, who is also a good friend of mine and who is no more now. All of them used to support our activities immensely over a period of 3 to 4 decades. I also would like to express my sincere thanks to both the Ministry of Human Resources Development as well as the director of our institute to form such a center of excellence on laser and materials processing. Of course, I will give my experiences in my presentation, how I have started this, and then where I am going now in the direction of both laser materials processing as well as the advanced manufacturing. So let me start my presentation with a note on how, let me share my presentation, then I can just say something about it also. So my, let me first go into the sharing. Then I'm just getting into something else. Can I share this? Can you see this?
It's up now. It's up now.
Yeah. Can you see this? Yeah.
Yeah.
Yes, sir.
I'm just trying to use the window, but anyhow, let me go into that. So as Professor Satish said, mentioned already, I do not want to dwell on the basics of materials processing with lasers and the applications of lasers. I think by now you all know about it. But I wanted to take you through a journey which I have made over the last three and a half decades on this laser materials processing. First, I started my journey at IIT Bangalore when my professor has asked me to develop a setup for making a micron holes with ND glass laser, then NdArc laser. So I had to make a small precision translation stage. Even those days, he was planning to engrave fine grooves and for the photolithography. I did not know that he has asked me, okay, first thing is you make the laser to work in the TEM00 mode. In fact, I started reading the 2 books which I wanted to tell you on the principles of optics by Born and Wolf, and then solid state laser radiation by Feuchner. In fact, no, these are the books which have really motivated me to see that, okay, this is where the science and engineering comes into picture. Then I was in ISRO for a couple of years, but then I wanted to go out of the country to do my PhD, but then my parents did not allow me. Then I resigned from ISRO. I went to an industry where the laser materials processing, again, using the laser engraving of rubber printing sleeves, for flexographic printing machinery. It was almost, some 150 or 200 millimeter diameter rubber sleeve over which we had to make the designs by means of a microprocessor control systems. So there I was in charge for the carbon dioxide laser from coherent overlays. It was only 350 watts laser, but I was in charge, and after some time I felt that I'm doing a very routine stuff which I didn't want to do it, and I came and joined in the physics department where Professor Y.V.J.S. Murthy, who was also my co-guide, wanted to build the color center lasers to store the information. That's all optical memories. Why I'm saying all this stuff is in 1980s itself, people were talking about the optical memories and also the photolithography mask being made by the lasers, etc. And of course, now the technologies have improved quite dramatically, and then we talk in terms of nanometers and less than that one. So that fascinated me to work with one Professor V. Radhakrishnan, and I went and asked him, I wanted to do PhD. If you like, please allow me to work on the laser materials processing. I didn't know what problem I had to take it up, but then he said, okay, you just come to me and then I'll talk to you after 1 month or so. And during my 3 years of stay at the physics department of IIT, I had the opportunity to go to Lambda Physics and then spend a week, and I went and spent 2 days at University of Darmstadt, where Professor Paprove now at RWTH Aachen, and then Professor Herjiger, who was also working on the lasers. Then I went to University of Southern California, Professor Michael Maas, who was the director and who wrote a book on laser materials processing, and I spent a day with him. But then people thought that, okay, with all these contacts, I'll be leaving the country. But my always heart is here. I said, okay, let me work here. Then my guide has asked me, okay, you have some experience. Guide, Professor V. Radhakrishnan, has asked me, he said that you have a setup. I don't know what is the type of setup that you have in physics department. Can you drill a hole in a small abrasive grit? And then he has asked me to describe a line on a stone, which is a grinding stone, which all of you are aware. So I took it there, and then immediately within half a day, I just showed it to him. Then he said, why don't you make 3 lines with some spacing? Then he took it to the surface roughness tester with a special stylus. He looked at the profiles on both sides, undressed and then dressed. So then he said, okay, now you're going to work on something like a dressing. I didn't even know what is dressing, because I did my master's from IASC, where I took all the courses on the design, right from the solid mechanics to fluid mechanics to all of them. Then since I worked in the industry and I developed some laser autocollimator at ISRO, so all these things gave me confidence. Okay, let me put my thoughts and then do something on this particular problem. That's how this is basically invention in 1985 to 89. And during that time, I had the opportunity to interact with many of them, like Professor Stephen Malkin, who came here and then spent a week to 2 weeks. And then he said, if it is in USA, we would have turned into maybe some venture or something. I went to the industry like a carborundum. I just asked them, is there any way that we can collaborate it? But then they didn't do much. And they only gave some materials like silicon carbide grades and aluminum oxide grades. And with that, I did some experiments and finally produced, some research, papers. In fact, when I sent this paper to UK on precision engineering, so it came back saying that the others are venturing into a research wherein they don't have any idea about what is meant by dressing, etc. Whereas Professor Y.V.J.S. Murthy from the physics has forwarded, sent the paper as the corresponding other. Why I'm saying all this is the youngsters who are observing, and then those who have been experiencing it on the research, The translational research is not like a science-based research. The science-based research is only in the laboratory and we don't go beyond that. So since those days, my passion is always to build something. Then we did the interdisciplinary research project from the ICSR, that's called our consultancy cell. And we got a mechanic, we built the setup. What I'm going to show you is a very quick a tour through all of them. I'm not going to talk about these things because Professor Samuel has given enough technical insights into the laser material interaction, how the long waves to the short waves to the ultra short waves can penetrate into the material and form a very clean pulse. So I think that is all, you have seen it. But my intention is to tell the next generation of youngsters and the entrepreneurs to look at the translational research, which is going to create a wealth for any nation. And that's where I'm currently working on a variety of technologies with many, right from the doctors to the agricultural farmers to machine tool builders to the auto industries, to see how do we really make a mark in all these areas where the manufacturing is extremely important. It's not the service or it's not the other types of activities we do it like entertainment or a strategy or something like that. So hence what I did in this particular 15 to 20 slides is basically to tell you how do we move from basic research to a technology, and from the technology to the commercialization. And that's where we today talk about the translational research and development and technology development. So I took this case study basically to take you through this one, but at the end I'll also show you what are the other technologies we are developing it at the center, where we do the translation from the prototype to the a technology which can be showcased to somebody and then take to the commercial level. So I think all of you know the inventions and innovations. It's a very loosely used terms, like the people don't really give much importance to these two terms. But then if you Google it and then see that, you usually find out that what is invention, what is innovation. The invention is creating a new idea. It can come from through brainstorming sessions, or unlike minds when they meet each other, they can bring some new ideas and then say, can you try it out? And this is limited to, invention is basically done at the R&D, either at the university level or in the R&D labs of many industries. But you can patent it so as to feel that, okay, you have done something great. And after that, you don't do anything except publishing it and then getting the joy and then getting some recognition, etc. But innovation is entirely different. As you can see that the innovation requires enormous amount of commitment to take this idea into reality. And that's where the trouble starts. So it spreads across various entities, right from the design, manufacturing, assembly, testing, etc. And similarly, in any organization, it spreads across the organization. So that means when the innovation is when the idea not only be proved workable, but also requires to be economically feasible. So that's where I'll give my own experiences in laser dressing. Without our knowledge and without having some insights into the business, so we tend to think normally that, okay, the idea is commercially viable. We argue and counter-argue with many of them and thinking that it will definitely work well. But then to take it to the commercial level, a lot of effort is needed. And that's where you can see how we have been working on it. I think all of you might be aware of this sort of flow of information and the various levels of the technology readiness levels. So as you can see that there are three parts. One is academia part, collaboration, and industry. And academia can do only that much because they can showcase some results by converting these ideas into a small lab level prototypes. I think through that we think that we have achieved a great thing, but then technology demonstration requires some collaboration. I will show you how we have collaborated, and Professor Ranga Kumandori was also instrumental in taking me and then asking one of the R&D establishment in machine tools in Bangalore to say, let us have some collaboration. And unfortunately, after a few years, he passed away. Otherwise, we would have done much more than what we have done at the moment. So the technology development and prototyping is another aspect which we need to demonstrate it before we move to the next level of commercialization. For the commercialization, definitely the industry has to play an important role unless they put their heart and soul, put their money, and then put their effort in marketing and then promoting it. I don't think that we can really achieve anything. Even though Professor Satish was mentioning that taking it to that level requires an enormous amount of effort from the industry, government, and other agencies also. This is where I have been interacting with many labs in India itself. They find it difficult to get connected with the industry. And again, it requires an enormous amount of effort from many sites. I will quickly take it through my presentation wherein, see, when my guide said that we'll go through the dressing of grinding wheels, then the first thing I did was diamond dressing and laser dressing. So those days, people used to use only single point or a multi-point diamond dressers. I think some of you who don't know about anything about it, don't worry about it. I'll show some pictures from which you can also make out something. And while dressing the grinding wheel, you need to stop the production or interrupt the production. And this causes loss of productivity. And the another point is the wheel material is lost heavily. And this is more so in loaded grinding wheels. And hence, you are wasting a lot of wheel material and unnecessarily wheel gets consumed. So when it becomes smaller and smaller, you throw it. So this is where the sharpening of the wheels by means of a single point diamond dresser becomes highly inflexible. And another important point is when you are dressing it, you are rotating the wheel and moving the dresser across the width of the wheel. That produces the helical grooves. So I think why I'm talking this one is in order to really bring out analogy to a process which is already existing, you need to study the existing processes and see what improvements you can really make by this invention. So I think you can see at the top, the problem is the grids wear out and the wheel becomes blunt, and some soft materials when you are grinding it, those chips will go into the pores and loads the wheel and also clogs the entire wheel. So this is where I found that the laser dressing is having a multiple benefits, unlike the diamond dressing or the multi-point dressers, etc. So one of the advantages of the laser is it's highly intense, and in this case, the intensity when it falls onto the grids get damaged. When they fall onto the bond gets damaged. And that is the concept. Though the wheel looks like a rough terrain, I was thinking that how do we really make use of the laser? But then my professor said that okay, yes, it is possible. Then immediately I got the clue that whatever may be the mode of the laser, whether it is a Gaussian mode or higher order modes, it doesn't really matter. The intensity of the laser is more important to create this sort of damage to the grit and bond. And then the other important point is non-contact, and we can always do in-process dressing, which can avoid any loss of production. And there is a less material removal because you are evaporating the material and forming the craters on the grit and bond. So hence you can see the wastage of material being less. And this is more important in case of a super abrasive wheels where you only one layer or a few layers. So of course, finally you can sharpen the wheel by means of helical grooves, by means of any type of pattern that you can produce it by scanning the laser on the wheel surface. And these are the things which I have really done it in my PhD. And when my thesis went to Milton C. Sharp and praised it, and then in fact, some part of my the investigations were included in his book, which was published after my thesis was defended. So why I'm saying all these things is a lot one can do it if you do this research in a very systematic way. And I'm going to show you all these TRL levels. Up to 6 only I could do because the industry is still hesitating to go in for this because they need to find some commercial value and the economic viability. I don't need to spend much time on each of them since I have given enough introduction to you on what I just plan to do it and how I did it. I'm going to show it to you right now. So if you just look at this particular diagram, so what I am showing you is the grit and bond, when they are, I think this is not moving down. So when you look at this particular aluminum oxide is a grit, and silicon carbide and CBN, like the cubic boron nitride, and all of them are grits. And we have different types of bonds like vitrified bond, resin bond, metallic bond, etc. So we took the conventional wheel of aluminum oxide and bond, use at several intensities, but I'm showing only one particular intensity. If you use at an intensity, that forms the crater. And here, if you look at the bond, it not only forms a crater, but it also shows up some sort of resolidified layer around this crater and with several cracks. So what we found was, okay, piercing through a grit produces sharp edges around that. And having this sort of a bond breakage and the resolidified layer with cracks, that can also allow the grits to fall off during the grinding after dusting it with the laser. So this is just a basic principle is actually proven by this fact. So then I just thought that, okay, we have to really prove beyond that. The TRL2 is basically, this concept has to be proved on the wheel, not on the grit and bond. So then he has asked me to take a small wheel and then see what happens to the topography. And as you can see that these topographies are seen on both small wheels and also large wheels. On the left hand side, it is a small wheels which are actually dressed by a small setup, and the large wheels are also dressed using the dressing system or a laser system available offline. It's not near the machine. If you wanted to really dress it, you have to bring the laser system to the machine, which is not possible. So I made a setup and then actually dressed the wheel. So what you see is a helical grooves very distinctly seen on the laser dressed wheel, but whereas on the diamond dressed wheel, you can see at the bottom, nothing is seen. So this is just another observation which we made it after we found that the lasers can be used. Then we made a setup, and this experimental setup is used in the physics department of our IIT. And then we also made a fixture. You can see that the entire thing we just made, and using the fixture we have dressed it and then shown that. The next step is you have to prove it in actual practice. So I can't say that this works. So the proof of concept was attempted by taking out the wheel, mounting it on the fixture, then dressing it. And we had to have some ingenious ways of putting it back, without any disturbance, like the wheel balancing and even statically and dynamically. So we had used some innovative ways of taking out the wheel with the mandrel and then putting it on the fixture. And as you can see that we just made a comparison with both the laser as well as the diamond dust wheels. And this comparison essentially gave us the confidence that it is possible to do it. Why? It is confidence because when you put the wheel along with its mandrel on the spindle of a machine, if it goes out of roundness and if it gives some eccentricity, the entire effort will go waste. It has happened once or twice. So what I'm saying is you need to have some ingenuity. That is called the engineering. So you have to put all of these thoughts into practice and get this. Then we also found these finish improvements. And though initially there were some hiccups, but then we said, okay, we can solve these problems. So why I'm saying all this is engineering is extremely important in order to really prove the concept. Otherwise, you think that these concepts will not work. That's where a lot of patience and the ingenuity is required. Then we went in for performance analysis of the laser dust wheel with the diamond dust wheel at different conditions. It is not enough if you choose one condition and publish a paper, but you need to choose a different diamond dressing conditions. And we mimicked all of them in the laser dressing and finally found that the laser dressing will give better performance in the and also the wheel life also will be much, much longer. I think these are all published and available in the literature. So hence I just wanted to really give you. So what happened in these 5 years of research is we proved the principle of laser dressing by means of the fundamental studies. And we also proved its validity by means of conducting these experiments offline. And then we also showed some other benefits of this laser dressing by grinding a austenitic stainless steel, which is a softer material, and then immediately it gets clogged. When the wheel gets clogged, so we just used the laser, and defocusing the laser, we could melt it and then remove this debris. And that's another application. Then the flexibility, instead of having a helical grooves, we made an axial grooves. So axially at an angle. So all these things also have helped. So you can just imagine how you can really develop this process if you have some sort of a real the idea that can be taken to this. So I think when in 2000, so I think almost 2 decades I tried, but I left it. But meanwhile, the CMTA was thinking of some collaboration with IIT. Then Professor Ranga Komanduri and other director also said that, okay, let us have some collaborations. They were looking for some ideas. And I said, why don't we try this laser dressing and make it into an online dressing? But here, the laser which I used was almost, it is a long pulse, about 450 microseconds. But here we have used this picosecond fiber laser and made an attachment as a part of our collaborative effort. Now we made it as an attachment on the machine itself. So why I'm saying this one is laboratory testing of this entire integrated system only will give you the confidence that you can move from the science to the engineering, from ideation to the technology, etc. So this, my students have used it and then published. And in fact, with Saint Gobain, we have had several interactions and discussions. And in fact, these are the various results we have generated by dressing a small wheels used in internal grinding applications. So I think if you have an idea which is original, I think you can generate lots of other results and the technologies also. And in this particular case, I'm showing you that we use various surface topography parameters, unlike the ones that we have used in 1985 to 1990, like S parameters, etc., using imaging systems. Then we also proved the effectiveness and the efficacy of the laser dressed wheels with online attachment. And these are all again published. So as you can see, the roughness values and everything, we need to do it like a G ratio. So what we did, whatever we have done has resulted into a setup which can be attached to any grinding machine tool. And you can also use this one for super abrasive grinding wheels. And now it will open up several other avenues when we are talking about high speed grinding and the creep feed grinding, etc. So this is where I feel that the efforts have gone up to technology readiness level 6 only. But I think after I have completed my PhD and I started working on the CNC machines and robots and other technologies, which are basically advanced manufacturing technologies. So we had the opportunity to interact with the industry and to develop a precision grinding machine. And that gave many industries a confidence that we can really build a center of excellence on machine tools and production technology as a translational R&D and commercializing these technologies. I think this is what our Professor Satish also was mentioning here. It is a 20% from the industry. They have to give the money upfront, and then only the government of India will give the money. And in fact, all the technologies which we initially thought of, 11 technologies, we have almost completed. And now we are thinking of several other technologies. So what are we here? See, we are not only doing the basic plus lab prototype at IIT and with so many students, we wanted to take it to the commercial level. And our focus is mostly on the machine tool and manufacturing sector. And we are actually doing several other things at our center over the last few years. And not only the machine tool building or automation, but we built several things, we patented them, and we are transferring these technologies also. And one of the technologies which is denied to India is developed, and then we took even international patents on transferring the technologies, which is basically a guideways or a slides and the spindles. Then we also converted a normal CNC lathe into a very precise lathe, wherein the precision levels have moved from 40 microns to 5 microns. And earlier it was giving about 40 to 50 microns error, but now we have almost started down to 5 microns with very few sensors, only 2 or 3 sensors And the entire machine can be converted with about 5 lakhs or less than 5 lakhs. And this has actually gives us the confidence of how to use the sensors, data, and then various actuators and compensate for these errors also. And the another project is basically robos. In fact, we started with the 6 kg and 10 kg are completed now. Yesterday only we have completed 25 kg. Now we are just trying to put them as a unit which can be used by many industries. And once they start using it, they can also give the feedback on the both precision as well as the reliability of these machines, which will give us another landscape for all of us. So this is another one. In fact, Professor Satish, myself, and Dr. Subbu, we have been discussing how do we build a framework for the process intelligence, which can be automated. And here we both use the data as well as the physics behind the process. And we have made only alpha version, and we are discussing with many auto industries to bring this technology into the limelight in the course of time. So I think these are all the various things we could do it. This happens only when you start thinking about the engineering and beyond engineering. Otherwise, we will keep staying only at the same spot without going further and without benefiting the society at large in course of time. So I think, though I just said that all these things can be done, but it is really tough. But you need to put an enormous amount of effort, and continuously you have to pursue your passion without any breaks. And we are also looking for many the young and the experienced people to see that this movement should go on to build the wealth, and then to build innovation ecosystem, etc. So thank you, Professor Satish. Yes.
Again, thank you so much, Dr. Babu. I think this was a fascinating reflection of your journey. Nonetheless, it's a remarkable pursuit of translation of a fundamental research to actual industry product that you kind of laid out so nicely. And there were questions related to the applications of lasers in the modern industry. I think this is a fantastic case study in that direction. Professor Babu and Professor Samuel, would you be ready to answer some of the questions that were posed in the chat line?
Yeah.
And yeah, I think there were some very interesting questions for all of us. The first one is basically there are people from different backgrounds. So they were asking what kind of opportunities exist for people beyond mechanical engineering, especially computer science, mathematics, and so on. Would you be able to answer that question first?
Yeah, so we have actually mathematicians and even computer science people have the application. Actually, the laser applications are being used in several of the components like MEMS components and other things which go into IC chips and all. But apart from that, on a theoretical side, actually they can use the modeling for making the models for laser matter interaction. So that's an interesting area where non-mechanical engineers can actually participate, especially like physics people, materials, and obviously even computer science people also can do that with a mathematical background.
So may I add something?
Yes.
Yes.
So actually, the modeling of each process is entirely different. If you talk about milliseconds to microseconds, the way the laser radiation interacts with the matter is entirely different. And again, if you look at the materials, you start from the soft materials, hard materials, plastics to the composites, to the metals, to the the alloys, and non-metals. See, I'll tell you, of course, the studies were attempted in the past, but then as new materials emerge, as new laser technologies like ultra-fast and the picoseconds. So understanding the physics is one aspect. Modeling them in order to choose the right set of parameters in operating these lasers for any manufacturing application is also equally important. And people attempt to do by means of a database study wherein you have to spend time, effort, energy, and even the lasers and others also will not be that reliable like the other technologies. So the modeling plays a very, very important role in all these side technologies to give the almost near optimal parameters or a broad window within which the other researchers can play with. So I feel that both physics and the other mathematicians can play. I think if you go into the ultra fast, you go into the plasma. If you talk about the plasma generation and shock wave generations, the shock wave we have to go into the gas dynamics, to the plasma generation into the plasma physics. Just imagine that all these theories are already studied, but then still there is a long way to go in order to build the robust models. Then only we can convert them into software, and then only it will become a package, and then the industries can use it for building such lasers. In India, only very few people are working on such. One is Shahjahanand lasers, but again, it is like some sort of a initial stages only. So I'll tell you, computational as well as the physics-based studies are extremely important for many of these things, because it is an energy source. You can do many things with it. In the same way that you can use your physics and the maths also to formulate some equations and build the models also. That's my feeling. Thank you.
Yeah, that's a great point. Actually, I'm reminded of the comment that my mentor, Professor Ranga Kumanduri, makes often. Manufacturing inherently is an interdisciplinary endeavor. And he exemplified that in the fact that when we actually form as a group and meet as a group, we will have Professor Lionel Raff, who is actually a physical chemist, as well as Professor Marty Hagen, who actually has built the toolbox, MATLAB toolbox for neural networks, and also people from physics and computations, all of them sitting together to address some deeper problems. So modeling is an important facet, as Professor Babu and Professor Samuel have mentioned. And also, if you think about how the processing technologies are evolving, many of these processing systems and machine tools are trying to deliver energy in a closed loop fashion, right? So when you look at developing closed loop and real-time systems, the controls, the underlying software systems, and their reliability, everything becomes extremely paramount. So I think there is a lot of roles for people beyond traditional manufacturing to be able to make impact in this area. That's a great question and fantastic answers from both professors. Thank you so much.
Thank you.
Yeah, and there were a couple of other questions too. I think in the interest of time, I will be picking, and then unfortunately, I will be leaving out some of the questions. Maybe many of them are very good. Maybe people can take this offline, and then I'm sure professors will be very glad to answer many of these questions. And the first one, the other thing is, what are the implications of these laser systems in the defense sector, especially in the strategic sector? So the question was, how will these technologies be helpful for India in defense sector?
I think I would like to give some insights into this one, since I've been associated with many of them, since my journey in 1980s, when my professor was interacting with some of them. In fact, the pollution detection, like a LiDAR. And then if you go into the underwater laser imaging, now all these things are the defense-oriented applications. Though we may think that it is a LiDAR is a replacement of a radar, etc. The aerosol formation, the cloud formation, and pollution, all these things, and chemical, reactions, etc. You can study. So, of course, there are several, those of you who are familiar with those things like a BARC. I remember one Dr. Bavalkar, he was the guy who has built the laser laboratory. We used to interact with him in those days. But now RR CAT indoor, they're developing lots of lasers. See, one of the major issue which we have been facing in any sector, either defense or strategic, and this is very, very conservatively kept in the hands of only very few because of the strategic nature of these areas. And unless we open up and then give it to the large number of people in a way that can be formulated. I'm not saying that you should tell the problem, and then come to academician or a student. Unless you package that one in a way that you will not lose your confidentiality or strategic nature, but at the same time you have to turn around and then say that this is what we wanted it from the institutions or R&D establishment. So that is where I think immense benefits can emerge from the collaborations with all these research laboratories in India, either a defense or RRCAT or a BRC or IGCAR, any of them I'll take. So probably we need to relook at it in view of the recent happenings in geopolitical scenario. Unless we seriously look at them, then we may not be able to develop these technologies and compete with anybody. The competition is good for any nation. It is not that the competition is bad. So that the entire society will benefit through this competition, rather than keeping it to only one set of industries or countries. I think that's where we have to look at it in a more broader manner to see the collaborations will definitely yield some immense benefits to the society in the long run. And offshoots are many, which we keep discussing, but then when it comes to the reality that the collaborations do not happen because of some conservative nature of the organizations and the government policies, etc. So that is my answer. Okay.
Thank you, Professor Babu. That was a very precise response. At this stage, I think we are coming to the close of this session. And at this point, I would like to thank both speakers, Professor Babu as well as Professor Samuel, for their wonderful address. And then it was very enriching for me sitting here from actually halfway across the earth. And glad to learn your journeys as well as the remarks. And let me turn it over to Professor Samuel at this point for his concluding remarks. Professor Samuel.
Yeah, we thank you all the participants for taking time to join and then interact with us. So we thank Professor Satish Bukkapatnam for taking time. It's early morning there, and Professor has taken time to collaborate with us, and also to be the moderator for this first webinar in our COE. So we thank Professor Ramesh Babu sir for sharing his experiences. So we also thank all our collaborators who have joined. Professor V. Radhakrishnan, who is actually the guide for Professor Ramesh Babu, has joined. Professor Shanmugam, who has been my PhD guide, he also joined. Professor Ling Su Kong from Australia, Professor Dong Bin Wee from Australia, UTS, and then Professor Koichi Sasaki from Japan, and Dr. Ravi Bate from ARC Hyderabad. So all of them have joined and encouraged us, so we'd like to thank them. So now we'll hand over to the organizing team for a formal thanking and closing of this meeting. Thank you all.
Thank you, Professor. Thank you, Professor Satish, for moderating this session so wonderfully. For sure, I have to be thanking Professor Samuel and Professor Ramesh Babu for conducting this session. Indeed, to comment, it was really very interesting to know about the facts that the research workings that you have shared. So as Professor Samuel commented initially, it was so beautiful that, so he's so fascinated about the lasers in the childhood. And I have to mention here that every kid in their childhood is so fascinated about the laser. And we are with you, sir. Let me go to the announcement. For the certificates, the participants should be attending a minimum of 20 webinars, and they have to compulsory mark the attendance. Without that, the issuing of certificates will not be considered. Also, it is advisable to come in the same username and use same email ID for an error-free attendance. And also, the Office of Global Engagement is working on this so that your certificates will be issued post this IRIS webinar series. Thank you once again. Thank you for attending.
So thank you, Professor Satish and other professors who have joined this webinar. So it's really nice that we have taken out this on very well. Okay, thank you.
Yes, it's so nice to see you all again. Hopefully we can meet in person sooner than later. And have a wonderful day everyone.
Thank you.
Thank you.
Thank you all.
Thank you
Yeah.
all.
Thank you. Bye. Yes, yeah.